Welcome to the third module, where we will be actually dealing with the geometry of surfaces. But before that, let us have some example in hands. So, I will do two typical examples, and most of the surfaces are special cases of it, these two examples. And for our course, we do not need more than this, because if you want to develop things in the more general form of general surfaces, then we will need more vocabulary, more languages, which as I said we will avoid. So, I will write on this example and parameterization on the screen, and I will draw the picture on the board for this lecture. So, first class of example we will deal with is ruled surfaces. A ruled surface S is just union of straight lines, they are called the ruling of S. If I define it like this, it makes no sense perhaps, but it is like this. So, suppose you look at the surface S and gamma is a curve, let us say gamma from alpha beta to R3, and it is regular, smooth, and gamma meets every ruling, that is every straight lines on S okay. So, what is happening here? I mean, so surfaces consist of kind of line like this, all the lines are there, and I have a curve gamma like this, and gamma meets every straight line at some point, say Q. Surface consists of this straight line. So, everything is there, I am drawing it by shade. Then any point P, I write delta here, I explain what it is. Straight line on S, P be a typical point on S. What I mean here, that gamma is like this, intersects one of the straight line at Q, P is a typical point which is a direction delta. That is delta u is a non-zero vector in the direction of the line passing through gamma u. Then a typical point P, if I write that parametrization, it will be gamma u, sigma u is gamma u plus V plus gamma u. So, what is happening here? This is straight line intersect at Q, P is the vector, P is any point on the surface, delta u is the direction on which P lies, then sigma u v is gamma u plus v delta u. So, you translate this kind of curve along all the rulings. So, these are the rulings of the surface. All these straight lines are rulings, and you are translating along every rulings, you get a point P, and if you translate around the direction gamma u, you will get a point like this. The thing is that when it is regular, okay, for regularity condition, let us see. So, what we need? Gamma u, this is gamma du plus v into d delta du, correct? And gamma v is simply v. Sorry, v is gone, delta u. So, I must have for regularity this vector not equal to 0, and you can easily check, that means that this is gamma u d gamma du, d gamma du, let me write it as gamma dot u. If these two vectors are independent, then of course, the cross product will be non-zero. And I put it as a simple exercise, I mean it is contained in the statement. This means and tangent to the rulings means what? Rulings are straight line. So, there gamma u will be never be parallel to any of the rulings. If it is parallel, then I will not have this, and I will not have this gamma u and del u are gamma dot u and del u are independent. So, this is the regularity condition, and for regularity condition this is what I need. Please remember this example, this is a very typical example, and we can generate lot of example of surfaces out of this, and this is a very generic example. I will show you with two more special cases of this, mainly so special cases of ruling surface. First one is generalized cylinder. So, again since ruling surface, it has to be union of straight line, so my curve gamma is from some interval alpha beta to R3, x is a vector in R3, let us take unit vector and you translate gamma in the direction of x to generate surface S. What is happening here? So, it is a special case of ruling surface, what I said. What I am doing here is, so let us take a simpler looking curve, so that take this curve and let us take x to be this vector, unit vector. This is unit vector gives the direction. So, I take this direction. So, I translate this curve gamma along x. So, what will happen? Something will go up along parallel to x, things will go down along parallel to x. The curve will remain 7 and then I will get a surface like this. And this will have obvious parametrization of that, suppose sorry, should not put the bracket, v dot x u in alpha beta and v in r. And let us say for regularity, what is sigma u? It is d gamma du yeah, and sigma v is just x. So, for regularity, that is sigma v not equal to 0, I must have d gamma du is never parallel to x, then I will have a cross product as a non-zero vector. So, this surface is regular provided the condition I wrote. This parametrization parametrization becomes really simple if I take a simpler form. But if I take, say, let us say in the x-z plane, I take gamma this is a curve in x-z plane and x to be z axis. Then I transform this, what I get? A figure like this. So, in particular, if I take gamma u to be cos u 0 sin u, then I get sigma u v equal to cos u sin u v, which is actually cylinder. So, therefore, this particular type of transformation is called generalized cylinder. But on the other hand, if you take any curve for that matter, by transformation you can put it in the z plane by rigid motion, and you can take the line of rotation, line of translation to be z axis, and so all the surfaces like this will be homeomorphic to generalized cylinder, provided your gamma is smooth and your axis is satisfies the regularity condition. Remember this, I will not repeat it. This may be very important for your exam. Another example of ruling surface is generalized cone. We have done this example before. So, this is a surface S, this is union of straight lines passing through a fixed point P and points of a fixed curve gamma, which gamma is regular curve, okay, regular smooth curve. And parameterization is very easy to realize, 1 minus V p plus V gamma u. What is happening here? I draw the picture on the board. So, we have a curve gamma out here and I have a point P. Okay. So, I am looking at all and I look at a point on the gamma, I look at all the straight lines that passes through P and some points on gamma. So, I will have a surface like this, and we have seen that this looks like a double cone, but a double cone is not a surface, that we have done last week. So, I have to remove this point P. So, the surface S is that rulings minus the point P. I have to remove the point P, otherwise I will not get a regular surface, because we have seen it that if I have this double cone type picture, then there is a problem. So, I have to remove the point P and then I will get what is called a generalized cone known as double cone. And again, if you see, I mean, this picture can be made very simpler in the sense that you take P to be the origin and some point on the z axis, let us say z equal to 1, and you take the curve which is passing through this, then you will have a cone like this. You have to remove the origin, this is your S, and I will leave you to calculate the sigma u and sigma v to see. I mean, in this case, in the simpler picture case, sigma u v is actually v f u g u, let us say z equal to, here we have z equal to z naught, that will be a simpler parameterization. So, this is about the ruling surface which gives double cone and also gives generalized cylinder. Next example of surfaces, general example of surfaces, what I am to do is surfaces of revolution, and this is the most important for applications. So, what we are doing here? So, you take a plane curve, it is called the profile curve, and then rotate it around a straight line. This will generate a surface, right? What will happen here? I take the most simplest example. Let us say I have a curve gamma on the xz plane. Okay, and I rotate it around z axis. What will happen? A typical point here will rotate like this and come here. So, the surface I will have is this, and very naturally I will have the parameterization as correct. You can easily verify this is a regular surface, that is not a problem. You can calculate sigma u, calculate sigma v, and then you see sigma u cross sigma v. This is nothing but it comes out to be how much? F square df du square plus dg du dv square. So, to be regular surface I must have uh, f square u. So, regularity condition is f u not equal to 0, and this fellow never goes 0, never goes 0 means gamma is regular. This is the tangent vector at gamma, because gamma is this fellow. But this surface actually gives us a lots of examples, and we will see some of the complications here in this week and also next week, that how to deal with such a surface. And when you do the geometry, there will be certain forms associated to surface and certain curves which are called geodesics associated to surfaces, and for this kind of surfaces with different kind of gamma or different gamma, the calculation of geodesics, calculations of forms may become really difficult. But this is a very general form, and we will see many application of it. So, I just write the parametric form for your record. So, gamma u is a curve f u 0 g u, curve in xz plane, f and g smooth, gamma regular, that is gamma dot not equal to 0 for all u, and then this surface I am looking at is f u cos v, f u sin v, g u, u belongs to where gamma alpha beta and v in 0 to 2 pi. This is surface of revolution. So, remember it. We will have many occasions in next 9 lectures to discuss about it. Thank you.